What's trickier is going onto the conductors. Shouldn't it be perpendicular to the conductors? Yeah, this is a line of equipotential too. It's 0 volts, right? So it should come onto this guy perpendicular. And then, you have to decide what's it going to do, right? It's going to come onto that guy perpendicular. What's it going to do here? Does it go, I don't know, it's headed this way. Does it curve like that? Don't worry too much about connecting it to the conductors, right? So try something simple like this. I would do something like maybe like this and like this, or you could try a couple parallel plates, right? Then I want you to try, once you've done something simple, try something a little more complex, like put a plate here and a plate here. Maybe try tilting the plates. One other fun thing you can do is put a conductor in here. What's that going to do? What do you suppose has to be true about the voltage at every point on that conductor? Can it be different? No, if it's different, charge moves and then it's the same, correct? So this is basically, if you think of that sheet of rubber, the sheet of rubber is a slanting thing, right? But a conductor in the middle is actually a level playing field. So it's like a large sloping hill that you've cut a soccer field into, right? If you go to Forest Heights Elementary School, it's like this sloping piece of land, right? And then they've cut the field into the hill, right? So it's gonna cut into it. These lines of equal potential are gonna bend around it like that, right? Right, it's gonna do that around it. Yeah. You're going to pick the voltage. When you move the probe this way, the voltage will change, and you'll pick the voltages that I told you to pick, which are 1.8, 2.8, 3.8, 4.8, 5.8. Yeah? Okay. Oh, yeah. Yeah, so to pick 1, 2, 3, 4, and 5, you actually have to go 0.8 more because of, read the thing, right? Because of electrochemistry, just putting graphite and zinc together in water creates a potential of 0.8 volts, even if you don't have the power supply hooked up. Yeah? So these voltages will be maintained by a regulated power supply. So yeah, read the directions like that, right? Okay. And then read the directions. You want to mark where the electrodes are. So just trace where they are on the paper. So if you bump them, you can put them back, right? And now mark gently on the paper points or so for every volt. Yeah, you can just read that, right? Okay. And then we're going to set up a little drying counter. Okay. Let me show you what the paper is going to look like once you get it. I have an example. Please wait. I don't want to wait. No me gusta waiting. All right. As you can clearly see, I labeled it Murray. Can we see anything on there? Yeah, I can see some dots there. See these dots? Like that? Okay. So I traced out where the plate is like this. There's a set of dots that go like this. And I'm just going to connect these guys. And then there's some dots that go. Remember, I'm a professional, so you might not... Hey,
Marie, what's the German phrase?
Oh, I'll teach you that. And then here's my other electrode here. And then... like that. This one's labeled 0 volts. This one, somewhat curiously, is marked 12 volts. I think I decided to go with 6 volts because that way it hurt a lot less to do the lab. Like the kids would only whimper a little bit when they're doing it. I'm just kidding, it's pretty safe. Okay. So there are my lines like that, right? And then the equipotential lines are going to come off of here like this, right? And somehow by the time I get there, I need to be perpendicular. See what I'm doing? I'm just kind of nuancing that. Yeah, look how good that was. Wasn't that amazing? Oh no. Okay, this guy here. I know I need to start. It helps to just, these are all curves. Is that good? That's almost good. Look at that, huh?
How do you know how to start, like, where to start?
What?
How do you know where and how far out to start?
Oh, just sort of try to space them evenly like that, yeah? Okay, now, one of the things says on your sheet, it says calculate the electric field at one of the points, okay? This is actually pretty simple, but you might want to write this down. Let's suppose this was 1.8, 2.8, 3.8, right? So this is really 2 volts, 3 volts, right? Okay. If I want to find the electric field here where it's most uniform, and uniform is where the lines are parallel to each other, all I do is I'm using the formula that E is V over X, right? And there's a minus sign that I ignore, right? And then I just measure this. This is 3.4 centimeters, right? This distance here. Right, so that's going to be 1 volt divided by 0.034, right? What everybody forgets to do when they do this calculation is they forget to turn the centimeters into meters. But you won't do that, will you? No. Okay. Anyway, that's that. Remember, for the Millikan lab, don't forget to get the size. Play around with it first, and then remember, you've got to have the size of the drop. You've got to free fall that, do that part 3 times, right? Then you can do zap and suspend, okay? We've got like 10 computers for that. We have 10 setups. There's like 40 of us, right? So what can we do? Probably if you're not working in the electric field mapping lab, you're out here helping people with taking turns on the computers. There's a few more computers we can set up, but I just haven't set them up, that we could do the Millikan lab on. Yes?
We don't have the Millikan lab software, and do it at home with worst case scenario?
Worst case scenario, yeah. All right.